Welcome to Maths with EJD. For now, this is about the last video. Oh, but okay. This is about the last video on partial differential equations per se. But then, I'm going to add videos from numerical analysis that deal with numerical solutions to partial differential equations. So, um, expect that. So we are talking about Navier-Stokes equations and fluid dynamics. And if we start out with that, we'll see this. We have an overview. The Navier-Stokes equations govern fluid motion, describing how velocity, pressure, density, and viscosity interact in fluids. And by fluids, we mean liquids and gases. Liquids and gases are generally considered as fluids. Okay, so the Navier-Stokes equations are fundamental to fluid dynamics. Capturing behaviors from laminar flow to turbulent chaos. To turbulent chaos. Okay. Now, let's look at the definition in mathematical terms. So the Navier-Stokes equations are a set. So we have a set of non-linear PDEs, and that's what we're talking about. Since we're talking about partial differential equations, there are a set of non-linear partial differential equations, PDEs, derived from Newton's second law. Newton's second law, which tells us that Newton's second law, which tells us that mass times acceleration will give us some forces. Or forces can always be expressed as the product of mass and acceleration. So it's derived from Newton's second law. Mass times acceleration equals forces. Okay. Applied to fluid elements. Okay. Now, for an incompressible fluid, for an incompressible fluid with so an incompressible fluid simply has constant density. For an incompressible fluid, meaning that we have constant density, they take the form one, we have the momentum equation. Momentum equation talking about the vector form that gives us rho into partial u partial t plus u dot grad u out here, and that is equal to minus grad p plus mu grad squared u. Of course, that's like the Laplacian, then plus a particular f. So we have the momentum equation, and here we need to know that rho is the fluid density, rho is the fluid density, u is the velocity vector, velocity vector. So in that, if it's in one dimension, that's only u. If it's in two dimensions, we have uv. In three dimensions, we have uvw. So it all depends. Then you have t, of course, that talks about time. Then you have grad, that is the gradient operator. That tells us we need to differentiate, right? That's the gradient operator. We have P. I think we have P somewhere. Yeah, there's P here. So P and rho, of course, they are different. So watch out. So we have P, which is pressure. P is the pressure. Then we have mu, which is the dynamic viscosity. Dynamic viscosity. Then we have F, which represents external forces. So, like gravity, external forces, e.g., gravity. Okay. So, I mean, that F kind of makes the expression non-homogeneous. So, meaning that it's some kind of external forcing. So, if you look at the left-hand side, the left side, that's where you have mass times acceleration. Mass times acceleration, which is the same thing as unsteady plus convective terms. Unsteady plus convective terms. Okay, so that's the left-hand side. So this is what that represents. Mass times acceleration. Okay, now you already know that u is okay, u is velocity vector, right? So the u dt automatically talks about acceleration. Okay, then we have the right side. So the right side talks about the forces. So mass times acceleration is equal to forces, right? So on the right, we have all the forces put together. That's talking about the pressure, the viscosity, at the viscous force and the external force. So pressure, then the viscosity, like we saw the other time. Dynamic viscosity is there, and then we have the external force. So you have mass times acceleration on the left and the forces on the right. So that's forces like pressure, viscous force, and external force F. So you have those on the right hand side. You have those on the right hand side. Okay, so um that's one of the equations, momentum equation. And then we go for the second one, which is the continuity. You know, we said the Navier-Stokes equations are a set of equations, right? So part of the equation is that first one with the momentum equation. So next we have the continuity equation, the continuity equation, and this is the mass conservation. So continuity equation. So if you have for mass conservation, mass conservation, an incompressible fluid where the incompressible, right? So for incompressible, don't forget it. That means we have constant density, right? Mass conservation and incompressible. So that means the grad dot u is equal to 0 because we have constant density. So this ensures, so it ensures no fluid, no fluid is created or destroyed. So that's why we say so we have conservation there, and the fluid is incompressible. So let's talk about the physical meaning of this. So we have the momentum equation, and of course the continuity equation, as you can see already. Okay, let's talk about the physical meaning of all this. So physical meaning of the equations now. So first of all, the momentum equation, that's the first equation up there. The momentum equation balances fluid acceleration. It balances fluid acceleration with forces. Forces like so you have pressure gradients. The pressure gradients push fluid, that then viscosity resists shearing. Viscosity resists shearing. And external forces like gravity, like we said, like gravity actually do their thing, they act too. Then another point is that the continuity equation, that is grad dot u equals 0, the continuity equation enforces incompressibility. 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 So the continuity equation enforces incompressibility, meaning velocity divergences velocity divergences vanish. Velocity divergences actually vanish. Then we have the next non-linearity. So we have non-linearity in, so you see u dot grad u. So this u multiply together ensures non-linearity. So non-linearity makes solutions complex. Now you will notice that from the very, I mean, since we've started talking about differential equations, linear equations are easier to handle compared to non-linear equations. So non-linearity uh, makes solutions complex. Makes solutions complex. Okay, especially in turbulence. In turbulence, where small perturbations, where small perturbations amplify chaotically. Chaotically. So, I mean, the idea of turbulence is, imagine a gentle stream flowing, but then turbulence is like you have a very serious dam, with the water gushing out. So those can be very simple ideas of turbulence, and you're going to see these different things as we go on. So let's talk about turbulence proper now. Turbulence. So what is turbulence all about? I mean, from the English word itself, it's like trouble, right? Like you have a lot going on, so to speak. That's turbulence. So first of all, turbulence arises at high Reynolds number. So Reynolds number determines uh whether there's turbulence or not. Turbulence arises at high Reynolds numbers. And Reynolds numbers are simply given as RE equals rho U L all over mu. Rho U L all over mu, where inertial forces dominate viscous damping. Viscous damping. So you remember all those terms before. So you rho UL all over mu. Okay. So that is how we get to talk. So high Reynolds number means there's turbulent flow. Then turbulence is also characterized. It is characterized by chaotic multi-scale, chaotic multi-scale eddies. It's challenging. It is challenging. It is challenging to predict analytically, of course, because of the non-linearity. It is challenging to predict analytically due to the equations non-linearity. Okay, so let's move over to this place. So let's talk about key concepts now. We're talking about Navier-Stokes equation and fluid dynamics. So key concepts, after which we take some examples. So look at some key concepts. First of all, we have laminar versus turbulent flow. So I haven't talked about turbulence just now. Let's talk about laminar versus turbulent flow. Okay, so first off, laminar means smooth, okay? Smooth, orderly. So it's orderly flow and it has low Reynolds number, all right? And examples include syrup, you can take medicine in form of syrup. So you have syrup flowing, so it flows gently, you know, um, because the viscosity is kind of high, so the flow is low. Then you have what you call turbulent flow. Turbulent. So for turbulent flow, what do you have? It's chaotic, okay? Like the example I gave before, you have like the ocean, like they're moving fast, or even a very like a waterfall kind of thing. Then there is mixing. So because of the speed, there is mixing, and because the Reynolds number is high, so you have high Reynolds number. A very good example would be river rapids. River rapids. Okay, so a fast flowing river. It's a very good example of a turbulent flow. So let's go talk about boundary conditions now. Boundary conditions. Boundary conditions. Okay, so we can have a no slip boundary condition. So that means that fluid velocity, at solid walls, fluid velocity at solid walls equals wall velocity. And of course, the wall is usually not moving, if so for an unmoving wall, the velocity is usually 0. So no slip happens in that situation, no slip boundary. Then you have inflow or outflow boundaries. This is specific. So here you have specified velocity or pressure at boundaries. Specified velocity of or pressure at boundaries. Okay. So you have no slip, inflow or outflow as boundary types. Now let's talk about some simplifications. Okay, simplifications. So you have steady flow, steady flow. So steady flow happens when the velocity basically, because u is velocity when the acceleration is 0, right? The u dt is 0, and then you have 2D flow. You have 2D flow. So here you reduce variables. So you can here you reduce variables. So you can say, for instance, W is 0. That's like the third dimension is 0. Okay. Then you have what you call the Stokes flow. Stokes flow. So for Stokes flow, you neglect inertia. So neglect inertia such that a Reynolds number is far, far less than 1. It's way less than 1. So maybe like very close to 0. So neglect inertia for Reynolds less than 1 for viscous dominated cases. Viscous dominated cases. Like, I mean, I can imagine on engine oil, at the viscosity is so high, so the flow is very slow. Okay, that's Stokes flow. Now, having taken care of all of these ideas, can we take some examples as I move this here, this here, and then I go use, okay, let me go for blue this time now. So let this be blue. So this, now let's take some examples. Uh, let's see how we go. Example one, for instance, example one. So for example one, we are talking about laminar flow between parallel plates, between parallel plates. And that is what we call the Poiseuille flow. Okay, that's laminar flow between parallel plates. So you have parallel plates and you have very gentle flow in between them. So you have plates like this and you have gentle flows in between them like that. So the problem is such that we need to find the velocity profile and the velocity profile for an incompressible fluid between two infinite plates, two infinite parallel plates at y equals 0 and y equals h. That's from the beginning to the end, right? Y equals h, driven by a constant pressure gradient, pressure gradient, partial p partial t equals minus g, and g is greater than 0. Okay, so then assume steady two-dimensional flow with no external forces. So F is gone here, no external forces. So that's the problem for laminar flow between parallel plates, called the Poiseuille flow. Okay, so how do we advance with this? We go for step one. So step one, so we have to simplify Navier-Stokes. Simplify the Navier-Stokes equations. So in this case now, because we have steady flow, that tells us that partial U, partial T is 0 already. Don't forget the original Navier-Stokes equations, right? So partial U, partial T now, this is 0, okay? The next thing is that we have a 2D flow, meaning that we have U equals U of Y and then the other parts are gone. So you have a 2D flow. So a 2D flow, that means U is equal to, so we are considering U of Y 0, 0. Okay. So we don't have V and W. So it's a 2D flow. So here we say that velocity depends only, the velocity depends only on Y. That's why. So we have u and y alone. So 2D flow. Then next, we have no body forces, no body forces, meaning that just like in the question tells us that there's no external force, right? Like here, 2D flow with no external forces. So that tells us that F is equal to 0. The F we have in the original expression, if you remember very well, this F now is 0. Okay. Now that that is 0, um, okay, the next thing is we should also understand for continuity, grad dot u is partial u, partial x, and that is equal to 0. Okay, so that is satisfied for sure. Satisfied since u is only u of y. U is not a function of x, so that's fine. So we can then go ahead and see that momentum equation in x direction, of course, only y direction exists. So in x direction, it's going to be 0 on the left hand side. So we have 0 equals minus dp dx plus mu d squared u dy squared. Okay, so now since the p dx is equal to minus g, this becomes this becomes of course 0 equals minus g, okay, plus mu d squared u dy squared. So which means that we have mu, let me see, the pdx is minus g. The pdx is minus g. So yep, the pdx is minus g already. So this is going to be, so that it's automatically going to be plus g, right? So we have 0 equals plus g plus all that. So we have mu d squared u dy squared, all right? And that is equal to g. It has to be equal to minus g because this is going to become plus, and by the time we move it to the other side, it's going to be minus g. So yeah, so we have mu d squared u dy squared. Okay. I think that is it because we have minus here already, minus the pdx. Let's see from the original equation, should there be minus with that? The pdx. Okay, we have this grad p. So the pdx, since we're given the pdx, so there's minus, okay. So this has to be minus for sure. I want to be very clear about that. So the pdx is minus g, and this is already minus the pdx. So this is minus plus g, this becomes plus g, and then if you transfer that to the other side, so it becomes minus g. So this is good to go. So then so we can see that this is an ordinary differential equation. It's an ordinary differential equation since u is only a function of y. Okay, so in as much as I'm using partial symbols, it's this is an ordinary differential equation since u is just a function of y, right? So we go for step 2. So in step 2 now, we solve the ODE. Solve the ODE. So we solve the ODE. Again, don't forget we have mu d squared u dy squared. So we can write it this way because of uh the sign. I mean, because it's an ODE now. So u d squared u dy squared. So that'll be d squared u dy squared. I said u, it's mu. So that's minus g over mu. Okay? Minus g over mu. Now, so we need to integrate twice. Integrate twice. So if you integrate twice, the first integral, when you integrate the first time, you have du dy equals minus g over mu y plus constant c1. Then we integrate the second time. We now have u, which is a function of y, equals minus g over mu. Then now we have um, y squared over 2 plus c1y that was there before plus another constant 2. So this is what we have after integrating twice. Okay, I mean, we've done that a couple of times, so that's I'm not bothering so much to go into details. But if you have issues with uh, calculus, you may want to check out my playlist on basic calculus. So everything is elaborated from I mean, my approach on this channel is to take a topic from the very scratch and take it all the way down to the complex cases. So in step three, we have to apply boundary conditions. Apply boundary conditions. And we already have all of this in the question. The first boundary condition is there's no slip at y equals 0, meaning that u of 0 is equal to 0. Also, there's no slip at y equals h. That's the other end of the wall. So that means that, okay, that also means that u of h is also equal to 0. If that is the case, we can say that at y equals 0, this is our expression, right? We have to refer to this. So at y equals 0, we have u of 0 equals, since y is 0, I'll just go straight. This is 0 squared, so everything here will go, all right? Then y is also 0. Okay, all this will go and all this will go. We just have only c2 left, right? Uh, oh, I like that. C2 left, right? Okay, so we have u of 0 equals C2, and this is 0, right? So that simply means C2 is equal to 0. So that goes. So at y equals h, okay? If you see that again, at y equals h, so you have u of h equals, anyway, you see y, just change it to h, right? Um, Yeah. And we already know that C2 is 0, right? So we also factor in that idea. So you have U of H equals minus G over mu. Okay, minus G over mu. H squared, that was Y squared. Now over 2 plus C1Y, which is H, and C2, which was 0. And all of this is also still equal to 0. So in this case now, we can have, this implies that we have this, right? So we have minus, we want to find a constant C1, right? Minus G over mu H squared over 2 plus C1H is equal to 0. So that means that C1H is equal to G over mu H squared over 2. So meaning that, okay, this H can cancel one H here. So C1 is simply equal to half G over mu. Okay, so we have C1 to be that. So C2 is 0, but C1 is half G over mu. Okay, so in that case, we can go back to where we are coming from. So the u of y, remember, the u of y we had was u of y minus g over mu y squared over 2. Okay, so minus g over mu y squared over 2. Okay, then we'll put the constants, right? Then what's the next thing? Then plus c1y, okay? Plus c1y. Now c1 is half gu. So that is plus c1 now is 1 over 2 g over mu y. Okay, so we have all of this. And of course, C2 is 0, so we don't worry anymore. So I can rearrange this and say u of y is equal to half g over mu y minus g over mu y squared over 2 still. I mean, the half can still come out, right? So 1 over 2. So u of y is now 1 over 2 G over mu y into 1 minus y, like that. Okay, I think something is not adding up. Oh, yeah, I forgot this h. Okay, I forgot this h. C1 is half G over mu h. So that's G over mu h. So G over mu h. Yeah, so that's h minus y. This is h minus y. So that's h minus y. Now we can have this still. So u of y is half G over mu y over h into 1 minus y over h. So that makes it into some kind of logistic kind of expression. So we have this for u of y now. So in step 4, we can interpret what we have done. Step 4, interpret. Okay, so here we see that the velocity profile is parabolic. So when the expression is quadratic in nature, then we say it's parabolic. So you can say this is y times y. So that's y squared, right? So we can say it's parabolic. Velocity profile is parabolic and it's peaking. So it peaks at y equals h over 2. Peaks at y equals h over 2. Then next, maximum velocity. Maximum velocity is this. We have u max will be u of h over 2. So anywhere we see y, we just put h over 2. So we have anywhere you see y, put h over 2. So we have half into g over mu, then y. Anywhere you see y now, so that's h over 2 over h, right? Then 1 minus h over 2 over h again, because y is h over 2, right? So we can tidy that up. So we have u max to be equal to 1 over 2 times g over mu times h over 2 times 1 over h. I think that makes it easier. 1 minus h over 2 times 1 over h, like this. So this cancels out, this cancels out. So u max is equal to 1 over 4 g h over 2, right? 1 over 4. I think there's an h I'm missing out, right? So, yep. Is there an h I am missing out? So this is, yeah, I think we're good. Yes. Yeah, this GH. Yeah, I think we're good. But you want to check that to be very sure, so that in case I've made any mistakes. So this is 1 over 4 g over mu. Okay. What do we have else here again? So we have that into 1 minus half. Interesting. Yeah, that's 1 minus half. So that I'm still wondering about this h over 2. U of h over 2, right? H over 2. So the 2 goes down, the h cancels out. I think yes. So here we have half g over mu y into h, half g over mu. Yeah, I think that works. So 1 minus half there. So I just have a feeling that something is missing. But let's see. As far as I think it's good so far. 1 over 4 g over mu, okay, times 1 minus half, that's simply half, okay. So we have u max. The maximum velocity is now 1 over 4, I mean 1 over 8, because 4 times 2 is 8. 1 over 4 g over mu. And that is the maximum velocity of the flow. Hope there's no h missing. I just have a feeling there's an h missing somewhere. I don't know why. Yeah, guess we are good. H over 2. And h cancels out in each case, so we are good. Right. So now we go for the physical insight. What is the physical insight into all this we have done so far? Physical insight. So first of all, pressure gradient. Pressure gradient drives flow, then balanced by viscous shear. Viscous shear. Viscous shear. Viscous shear, not sharing like sharing. Shear here is more like tearing something, in a fluid, like you're breaking things apart, sort of. Okay. Then the next thing is that no slip, no slip, no slip conditions, force zero velocity at walls, creating a smooth gradient, creating a smooth gradient. That goes. All right. So that's one example. So let's see example 2. Example 2. So please check that up and be sure. I have a feeling some things might be wrong there. Stokes flow around a sphere. Stokes flow around a sphere. That's the second example we are taking. So the problem is to want to find the drag force, on a sphere of radius A moving at constant velocity u, through a viscous fluid, at very low Reynolds number. Very low Reynolds number is where R is far, far less than 1. Okay. So here we are using Stokes approximation. Use Stokes approximation. That is, you need to neglect inertial terms. Okay, that's what that tells us. So step 1. In fact, I think I should switch things up now. So let blue come here while I go for this one now. So step 1. So again, the first thing we do is simplify Navier-Stokes based on the conditions we have now. So Navier-Stokes is the general thing. Whenever you have a question, you simplify it based on the information you have. So we know that we have low Reynolds number. So in that case, we neglect the u dot grad u and du dt. So because of the low Reynolds number, the next thing is that it's incompressible, right? It's incompressible. Okay, because of the incompressibility, we know that del dot u equals 0 holds because it's incompressible. We also know for steady momentum equation, now, we have 0 to be equal to minus grad p plus mu grad squared. Mu grad squared U. Okay, so that goes, and then this is now the Stokes equation. This is the Stokes equation, linearizing. So this helps to linearize Navier-Stokes. Okay, that goes. So the next thing is to set up. So we go for step two. For step two, we talk about the setup now. Okay, so the first thing is talking about spherical coordinates. Spherical, we're talking about a sphere. So we need to talk about spherical coordinates. So we talk about sphere at origin, and then fluid velocity far away. Fluid velocity is far away from the origin. So it's more like you have a sphere. Do I still remember how to draw a sphere? I know it's basically built on a circle, and then you have you know, something like this. You have the radius, you know. It's been a long time trying to remember. So you have fluid flowing and all that. I'm sure I'm not doing a very good job with this, because the question is talking about the force on a sphere. They find a drag force on a sphere of radius, a moving at constant velocity through. So it's moving through a viscous fluid, you know. So you have the fluid flowing all around it. So of course we have this kind of radius, right? So spherical coordinates. So since we're talking about a sphere, spherical coordinates, sphere at origin, fluid, you have the sphere at the origin. The fluid velocity is far away. Uh, in that case, being far away, so you have u to be something like constant speed for u. Then you have as zero zero as r goes to infinity. The radius of the sphere approach goes to infinity, so to speak. So, and another thing is that the boundary boundary condition on sphere is something like r equals a, such that u is equal to 0, no slip. So there's no slip, and sphere moves, sphere moves, sphere moves with fluid frame. Okay. So lastly, we can now solve for you can solve for velocity velocity u and pressure p. Velocity u, pressure p. Basically, I think that's what is left here, so to speak. Then we go for the third step, step 3, which has the solution. Step 3. So we just summarize the solution. So solving Stokes equation, solving Stokes equation. Solution summary. It's just summary. We're not going into the detail. Solving Stokes equation in spherical coordinates. In spherical coordinates is complex. Okay, it's complex for sure, because it involves stream functions, stream functions, or vector potentials, or vector potentials. So the analytical solution, which is a Stokes law, gives the velocity and pressure fields, and pressure fields. So the key result is that the drag force, the drag force on the sphere the drag force on the sphere is FD equals 6 pi mu AU. 6 pi mu AU. U is the constant velocity we're given in the beginning. So this is what the drag force on the sphere ends up being. So in step 4, now we can talk about verifying. Step 4. So step 4, we verify. Verify. So here, drag depends linearly on viscosity, mu. As you can see, so there's a linear relationship between drag and viscosity mu. Then same with the radius A, and velocity big U. Okay, then it is also valid for Reynolds number far less than 1, very small Reynolds number, where viscous forces dominate. So viscous forces dominate. So the slow is very easy. So e.g., a droplet in syrup. So something very draggy, like engine oil even. A droplet, e.g., a droplet in syrup. Okay, so we have that. Now let's talk about physical insights now. Physical insights of all those examples. That's this example now. Physical insights. So for the physical insights, we have number 1, in Stokes flow, inertia is negligible. Inertia is negligible. So drag arises purely from viscous shear. Okay. 2, contrasts with high Reynolds number flows, high RA flows, e.g. aerodynamic drag, e.g. aerodynamic drag is directly proportional to the square of the velocity. So that's its contrast with that. Okay. Though I know it's a lot, but I just want to do a thorough job. So here I go black here. So back here. All right. So I go for example 3. Example 3. It's a long video, so no worries. So talk about turbulence and eddy viscosity. Turbulence and eddy viscosity. Okay. So here we want to estimate the effect of turbulence, on momentum transfer in a pipe flow with diameter d equals 0.1 meter, mean velocity u equals 5 meter per second. Then we have density rho equals 1000 kilogram per meter cube, and viscosity mu, which is 0.001 viscosity mu, which is 0.001 kilogram per meter second. So use the concept of eddy viscosity. So these are pointers to the kind of simplifications we need to do as usual. Use the concept of eddy viscosity. Eddy viscosity. Okay, so let's go for step one in this case. So step one, we compute Reynolds number. Compute Reynolds number. Compute Reynolds number. That's the first step here. So the Reynolds number RA is rho UD all over mu. Okay, so you know the other time we talked about length, but now it's given the diameter is a kind of length. So for sure, so we have rho now is 1000 times constant speed, the velocity is 5, and density diameter rather is 0.1 all over mu. That is the viscosity. That is 0.001. Okay, so of course that means that the Reynolds number is 1000 times 0.1. That's 100. 100 times 1000. That's no 1000 times 0.1. That's 100 times 5. That's 500 divided by 0.001. So we can move 3 steps. So if you have 500 times 500 dots, and then we have 0.001 like this. So so let's say dot 000 like that, right? So we can move 3 steps. That's 1, 2, 3. So we move 1, 2, 3. Okay. So it means that we have the Reynolds number to be 500,000. That's so large. So we are looking at a very turbulent flow. Okay. So we said now RE, because RE is far, far greater than 2,300. So flow is turbulent. Flow is turbulent. Okay. So there are classifications to know which flow is. So small flows are laminar, while high Reynolds numbers rather. High Reynolds number means turbulent flow. Reynolds number means laminar flow, slow flow, so to speak. So that's step one there. So step two. So for step two, we talk about turbulence characteristics. Turbulence characteristics. Turbulence characteristics. So here we have that turbulent flow features eddies transferring momentum across the pipe. Okay, then we also have across the pipe. Then we have eddy viscosity. Eddy viscosity mu T, I think mu T models enhanced mixing, because for turbulent flow mixing is high. Enhanced mixing, so that's much larger than molecular mu. Okay, and we go for step three. So step three, we estimate eddy viscosity. So here we say that in turbulent pipe flow, so we know mu T is approximately 0.01 rho UD. This is empirical mixing length model. Then we see that mu t mu t is approximately 0.01 times 1000 times 5 times 0.1, and that is simply 50 kilogram per meter per second. Okay, does that work? 1000, two zeros, one, yeah, three zeros gone, right? 0.01, then 1000 times 5 times 0.1. So 1, 2, 3, three zeros. So this should actually be 5, I think. It should be 5. I believe this is 5. So because two zeros gone, so we have 10 times this, that's gone also. So it should be 5 actually. I think it should be 5. Yeah, it should be 5. Okay, so next we compare. So we compare mu t over mu. That is like 5 all over 0. That should be 5 all over 0.001. That's mu of the, yeah, 001. So that means we have 3 zeros, 1, 2, 3. That's 5,000. So that's just 5,000 for viscosity, for the comparison. So it's 5,000 times. So showing that 5,000 showing turbulence dominates viscosity. Turbulence dominates viscosity. Okay. So we talk about the effective Navier-Stokes, step 4. So effective Navier-Stokes. Wow, this will be one of my longest videos, maybe. Effective Navier-Stokes. So in turbulence models, like what we have in the case of Reynolds averaged Navier-Stokes. So what we do is we replace the original viscosity with that viscosity plus the turbulent viscosity, so to speak. So we now have rho into du dt plus u dot grad multiplied by u equals minus grad p plus mu sub t grad squared u. Okay, the external force is not there. So here we now have here, since we have mu sub t to be far greater than mu, so viscous term is dominated. Viscous term is dominated by turbulent mixing. It's dominated by turbulent mixing. Okay, so talk about physical insight now. Physical insight. So here we see that turbulence enhances momentum diffusion. Of course, it enhances momentum diffusion because the flow is kind of violent. Momentum diffusion. Flattering velocity profiles compared to laminar flow. Okay, so then eddy viscosity simplifies. So we're told to use eddy viscosity, right? Eddy viscosity simplifies complex eddy interactions, complex eddy interactions into an effective viscosity, into an effective viscosity. Okay, so let's talk about turbulence in context now. I think this is really important. Okay, let me switch over to this black now while I go for this one. So turbulence in context. Turbulence in context. So first of all, we have the challenges. Challenges. Okay. So exact solutions. Exact solutions to Navier-Stokes. Exact solutions to Navier-Stokes for turbulent flows are infeasible. They are infeasible, okay, due to non-linearity, and chaotic scales So numerical simulations, e.g. DNS and LES or models, e.g. the K minus epsilon, approximate solutions will be necessary, right? In that case. So with that done, let's go for in real world now. In real world, so we have the fact that turbulence affects drag. So see in aircraft, e.g. we have mixing. Okay, as you see in aircraft, right? Turbulence affects drag, like we see in aircraft. Okay. Then it also affects mixing, as you see in combustion. It affects mixing, as you see in combustion, and even weather prediction. Weather prediction, it can be quite chaotic. Then example application. So we have in aerodynamics, turbulence models, predict lift and drag. So these are ideas in, aircraft navigation, balancing computational cost with accuracy. Okay. All right. In summary, I'm still going to show the Python code. I hope I don't forget. In summary, the Navier-Stokes equations unify fluid dynamics. So it's more like you have everything together in one place. Then you can now simplify based on your situation. Balancing inertia. Inertia is, of course, reluctance to motion or reluctance to reluctance to motion. Balancing inertia, pressure, viscosity, viscosity, and external forces, and external forces. So examples illustrate laminar flow. So where we have Poiseuille flow. Poiseuille flow shows parabolic profiles, so parabola there, parabolic profiles driven by pressure, parabolic profiles driven by pressure. Now we have Stokes flow. We are going to see some of this in the Python code. We have the Stokes flow. So that's low Reynolds number drag, which follows the Stokes law. Stokes law highlights. So this highlights viscous dominance. It highlights viscous dominance. So you have a turbulent viscous dominance, right? Then 3, we have turbulence at work. Turbulence. So for turbulence now, eddy viscosity captures enhanced mixing in high Reynolds number flows. Okay, so this cases, right? These cases span simple analytical solutions, they span simple analytical solutions. So there are some cases where we have simple analytical solutions to complex turbulent phenomena, grounding fluid dynamics, grounding fluid dynamics in practical understanding. Wow, this is such a lengthy video. If you followed up to this point, kudos. So, I mean, let's visualize this before we round off finally. Okay, so see this. So I'm going to show some different kinds of flows that we've talked about. Although I didn't talk about a lead-driven cavity flow, but I mean, it's good to see. So it's more like you have the lead of a container dictating how the flow goes. Okay, so lead-driven cavity flow. So, of course, you study the code later. I'm trying to save time. So, yeah, so you see that lead-driven cavity flow. So it's more like you have a fluid into a container and then it begins to flow around. So you can see the arrow going in that direction. Then just now we talk about Poiseuille and Stokes flows. So we are going to have the two together in one as you do this. So you see we have the Poiseuille profile, which is a laminar velocity flow. So very smooth kind of flow. But here you have velocity field with vortices for Stokes flow, So this yellow area shows where you have high velocity magnitude. But all those dark places are like maybe where you have very slow motion of fluid, but in the center you have you have the motion very seriously in that center right there. So that's how it's been with this particular PDE video, I think about the last, except something else comes up. Of course, I'm going to add the numerical solutions of partial differential equations after now. So this is how far we go for Navier-Stokes equations and fluid dynamics. It's a very long one for that matter. So let me know in the comment section how helpful these videos are for you. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. If you have not subscribed to the channel, please go ahead and do that. And don't forget to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content we have here. Till I come your way again, keep doing maths right. Bye.